Okay, just now we say, well, the lower bound possible for comparison sorts will be omega in log n. That is how low we can get or how fast we can get as long as we are doing the comparisons. And if we look back to the algorithms we have already covered, and you will know that for the heap sort and the merge sort, and they are already they have already reached the lowest bound possible for the comparison source, right? But in this lecture, we are talking about the sorting in linear time, and the question is how can we be better than omega in log n, and why it is possible? Okay, and then we need to see a new sorting algorithm, and that is the counting sort. And the very important thing about the counting sort is we are not doing comparisons. Okay, so if we want to come back to the question we have asked before, since we have already proven the lower bound possible, how do we break it? And the answer is we stop doing comparisons. We want to do counting or something else. We have to break some of the rule to be better than n log n, or be even lower than n log n. Okay, so well, but to do the counting sort, we have to add in a few more assumptions possible. And we are assuming that for all the numbers we are sorting, those are integer numbers, and they are in the range from 1 to n. Okay, so for the counting algorithm, we expect to have a from index 1 to index n, and for each of the a of the value in the array a, they are in the range 1, 2, 3, and da 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 to k. Okay, they're all integer numbers from 1 to k. And the output will be b 1 to n sorted. Well, it's not really a sorting in place algorithm. We are building a new array of b, and the array of b has exactly the same size to the array of a. And in addition, when we are doing the sorting on the fly, we will also create an array c, and this array c will have from 1 to k. So what's the k value? K value is the maximum number possible in the input, right? So this is an auxiliary storage we have to build when we are doing the sorting algorithm on the fly. Okay, so let's see the counting sort. We see 4 iterations. Okay, well, no worries. I'm gonna go through all the iterations one by one. Okay, and then let's work on this counting sort using this small example. As you can see, for the a, they are all integers, and the range will be from 1 to 4. Okay, and then we want to move to my drawing board. Okay, so we know this a is the example we want to work on, and then we have the k as 4. And remember, when we are gonna do other than a on the fly, we will also do the array of c and the array of b. And for the size of the array c, that depends on the k value. So since the k value is 4, and then the size of the array c will be 4. And how about B? B will be the sorted array. Okay, so since B is the sorted array, and the size of the B will be the same to the size of A, so there are 5 slots in the B. Okay, so let's see the first iteration. The first iteration is kind of simple. From 1 to K, we want to fill in all the Ci using 0. Okay, so there are only 4 slots, so let me just write down 4 zeros. Okay, so this is the result for the first iteration. We have all zeros. And then how about the second one? So for j, from 1 to n, we are doing the a, c, aj, and then plus 1. So what is aj? Aj is we want to grab a value from the a using the index as j, and then say if you want to get this one, if the j is 1, and then we are getting 4, so aj will be 4, and then c4 plus equals 1, so we want to change this value from 0 to 1. Okay, so this means that for the value 4, we have already counted and then put a 1 here saying I count a 4. And then if I move on to the next j value, it will be 1, it will be j is 2, and then a j will be a 1. So c1 plus equals 1, so we want to increase this value by 1. So we are gonna change this 0 to 1. So what does this mean? This means we have already touched this value, and then we have counted a 1 here. So the slot 1 counts a 1 here. And the next value 3. So j will be a 3, and then aj will be a 3, and c3 plus equals 1. So this value will be a 1. Okay, and then I'm going to put a check mark here. And the next value we have the 4. So j is 4, and then aj is a 4, and then c4 plus equals 1. So we want to change this to 2, saying so far we have already seen 2 fourths, and then another 3, and that is j is 5, and then aj is a 3, and then c3 plus equals 1. So I want to change this to a 2, saying so far we have counted 2 twos. Okay, so this is the version of the C after the second iteration. And what we have done is, since we have 4 slots, we are counting how many ones we have seen, how many twos we have seen, how many 3 we have seen, and how many fours we have seen. Okay, so far we have seen 1, 1, 0, 2, 2 threes, and then 2 fourths. Okay, so this is the version of the C on after the second iteration. And the next one, so for I starting from the 2 to k, and then we will do ci equals ci plus ci minus 1. Okay, we are starting from the 2 here. So we for this c2, we have the c2 plus c1. So instead of 0, we are going to do a 1 here. And then after that, we have c3 equals c3 plus c2. So this value, 2 plus 1, will have a 3. So 3 will be put here. And then we will have the C as a 4. So C4 equals C4 and plus a C3. So that is 3 plus 2 equals 5. And we are going to put a 5 there. Okay. And this will be the C after the third iteration. Okay, and then and you may ask, what is this C? How do I interpret this C? And hold tight, I'm going to explain after we when on the fly when we are doing the last iteration. Okay, and then we are going to do for J from n down to 1. So we are going down instead of going up in this case. So J equals n, and then remember n is 5. So we are gonna start n as 5, and in this case we are finally touching the B. What is B, by the way? B is the final sorted list, right? So in this case we are touching the B. So we are gonna start from the J. So J will be 5, and then AJ will be the last value, which is the 3 here, right? And then C3 will give you what? C3 will give you a 3. And then for the B with the 3, which is this slot. And for this slot, we want to plug in AJ. And what is J value? J value is a 5. So we are sending this 3 to this slot. And then we are going to reduce the CAJ by 1. So what is J value? J is 5. And then what is AJ? AJ is 3. So C3, we are going to reduce this value by 1. Okay, so this one will be reduced to a 2. Okay, So I want to stop here. We only run the first iteration of the fourth loop. And then what have we done? We are grabbing one of the last value from the A. And then we go to this slot. And this slot will tell me that if I see a 3, and then I'm gonna have the index array, and this index array will be the value that I plug in this 3. So let me explain another way. We are considering this version of the C as a dispatching table. This is the name that I gave it personally. So you don't see it anywhere, but this is an analogy I want to use. So if we see a 3, and then we will go to the corresponding slot in the C. And this C value will tell me where should this 3 be put in the final sorted list of B. And then we say, okay, I want to dispatch this 3 to this slot, which is index 3. Okay, so let's move on. Just now, we have seen the N as a 5. So now we want to go down. J will be 4 in this case. So what is AJ? AJ will be a 4. And then after that, C, and then what is the C4? C4 will be a 5. And then B5 will have the value of this 4. So we are dispatching this 4 using this value 5. This is the index 5. So we are dispatching this 4 into the index 5 of the B list. So we are going to put the 4 here. We are dispatching this 4 into here as the index 5. And then we want to reduce this value by 1. Okay, so when we are reducing this value by 1, now we have 4. What does this mean? This means that if we see another value of 4, this 4 will be dispatched here at the index 4. Okay, hold tight. We are going to see that later. And then we have the 3. So, we have this J as the 3. And then J3 will give you J will give you the 3 here. And then C3 will give you a 2. Okay, and then we are trying to dispatch this 3 into the index 2 here. So we are dispatching another 3, and then we want to reduce that again. This means, well, if we see one more 3, and then that 3 will be dispatched to the index 1. Are we going to have that? Actually, no. But anyhow, this is another 3 got dispatched into the list B. Okay, and then we move on. We want to touch this one, and for this one, and then it will tell me if you see a 1, and it should be dispatched into the index 1. So it will be put here, and then eventually we have a 4. And for this 4, and then since we okay, well, this one will be down to 0, by the way. And then we have 4, and then we go down here, and then we will see, okay, C, the dispatching table C will tell me if you see another 4, this 4 will be plugged in or dispatched into the index 4, so it should go here. Okay, so in the first 3 iterations of the counting sort, what we are doing is we want to build up this C, and this C will be a dispatching table. And depending on the corresponding value, and then we will go to the corresponding slot, and this C dispatching table will tell me if you see such a value, which slot will this value be dispatched into the list B. So, well, again, well, the dispatching table is just a name that created by myself, and I don't see the textbook or any textbook use this one. This is just an analogy that I want to show you the idea. So even though there are a total of 4 iterations in the counting sort, the first 3 iterations we build up the dispatching table, and in the last one we are making use of the dispatching table, which is C, and on the fly, if we have to, we also have to update the values of the dispatching table. So when we see the next value, we still know based on the updated dispatching table, we know how we are going to dispatch the next value. Okay, so that is the dispatching table, the idea of the dispatching table. And another thing I want to remind you is for this three, okay, this is the we have two threes in the final sorted list B, and then we have two threes in the A. So for this three value, where is it? Is this three value this one or this one? So think about that. If you want to check the original dispatching table, we have the three. So the first three here will be dispatched here. Why is that important? It's important because when we dispatch the second three, we dispatch it to be the second three in the sorted B. Okay, and the same thing here. Where is this 4? This 4 is here. So this 4 is the second 4 in the original list A, and then this 4 is also the second 4 in the final sorted list. Okay, that is also a very important feature in the counting sort. Okay, so let's go back to the PowerPoint. So, well, we have explained the C, and then we are building the dispatching table for the C. And then what is the running time? So the running time is kind of easy because in the first and the third iteration, we are running up to k times. And then in the second and the fourth iteration, we are running for up to n rounds. So the first we have two OK and another two ON, right? And then we just put them together, and then the total time will be the OK plus N. And usually, we assume that the K, which is the range of the values, the range of the integer values to be sorted, to be a ON. And then we will say, okay, this counting sort is a ON time sorting algorithm. Is that cool? Well, we say the sortings are omega n log n, and now we just be that. So is there a contradiction here? The answer is no, because when we say the sorting algorithms are omega n log n, we say we are only talking about comparison sorts. How about the counting sort? In the code of the counting sort, do you see any greater than, smaller than, greater or equals, smaller or equals? No, right? We don't see any of those comparisons. So this counting sort, it is not a comparison sort. Okay, since it is not a comparison sort, and then we are able to do even better than the omega n log n. So another thing, as we just discussed, well, the counting sort is stable. And being stable means if we see the second, if we see 2 fourths in the original list, and then the second 4 will be the second 4 in the final sorted list B. And then if we have 2 threes in the original list, and then again the second 3 will still be the second 3 in the final sorted version, and that is important. This means for the counting sort, this is a stable sorting algorithm. Okay, in other words, we can say if there is a tie of two values in the original list, and then the tie will be broken based on whichever value appears first. Okay, so counting sort, that is a stable sorting algorithm. And so what's the problem of the counting sort? In other words, since the counting sort is a linear time sorting algorithm, and we would expect people use the counting algorithm really a lot, but probably in the real world it's not really true. Why? Because it depends on the range of the k. Well, we are putting a very strong assumption. We are assuming that we are only sorting the integer values, and then for the k, which is the maximum of the value to be sorted, that is a O n. Well, only if this is true that we can do a counting sort. So let's imagine a really crazy case. Well, if we are trying to sort a 32-bit integer, Okay, and then what is going to happen? 32, a 32-bit integer, and then the maximum will be 2 power 32, and that is really a huge number. And if the k is such a huge number, what will be the problem? And remember, for the c, it depends on the value of k. So if k is such a big number, this means for the C, it will be a huge dispatching table. And building such a huge dispatching table will be super expensive simply because that K is too large. Okay? And then if you have a very small n and a really huge K value, and then our assumption of this part is not correct anymore. We are assuming that k is a O(n), but if you have only a few values, but the k is really large, and guess what? It is well, and then we can't really say this is an O(n) algorithm because k is much larger compared with n. So in this case, counting sort is not really the way to go. Usually we use the counting sort when the k is a relative small value, and then n is also reasonable, and we are only sorting the integer values. Okay, so in this video we talk about the counting sort, and counting sort is cool because we are doing the counting, we are not doing comparisons, so we are able to beat the n log n. However, you also want to remember that for the counting sort, we are putting on a lot of the constraints. So counting sort is cool, but we can only use that to sort the integer values when the k is not too large. That's the reason that the counting sort is cool, but it's not really used a lot. Okay, so that's it for this video, and in the next video we want to move on to reading sort. Okay, see you in the next video.